In this quest, we're going to talk about the sound interference in terms of beats and also the Doppler effect. So remember, sound waves interfere just the same way the other waves do. They add together. So if you get two peaks or two troughs at a time, you'll get constructive interference. If you have a peak and a trough together, they'll destroy each other and you'll get destructive interference. So depending where you're sitting in a room compared to speakers, you may or may not hear the sound very well. Waves can also interfere in time. So if you take two waves that have a slightly different frequency and you add them together, at some times they're going to interfere constructively, at other times they're going to interfere destructively. And you can see in the figure below what that means is that the intensity varies with time. And so if you look at the repeat time from where you get a loud sound, which is a high peak, to where you get a quiet sound, it's going to depend on the difference between the frequencies of the two sounds. So this picture here shows you sort of the envelope, that dashed line around there that shows you the from soft to loud oscillations. So what we hear with our ears is we hear the average frequency. So what we hear is the two frequencies together. So you add them together and divide by 2. And the amplitude is going to beat, it's going to go up and down in intensity at the difference between the two frequencies. So if they're different by 10 hertz, the sound is going to get loud and quiet 10 times a second. If it's different by 1 hertz, it's going to get loud and quiet 1 time a second. So this is why orchestras make sure they all tune up so that all the instruments are exactly in tune. Otherwise, when two different violins or two different other instruments play a sound at the same nominal frequency, you'll hear beating, you'll hear the intensity going up and down. The Doppler effect occurs when a source of sound moves with respect to an observer. And basically what it is you hear a different frequency depending on whether the source of the sound, so in this example it's a fire truck, is moving towards you or away from you. So if the fire truck is stationary, those sound waves have a fixed wavelength, a fixed distance apart. And so when you're standing there, you hear the waves pass you at a certain time intervals, and it doesn't matter which side of the fire truck you're standing on. If the fire truck is moving, then what's happening is that those sound waves get compressed together, and so you're going to hear them come past you more often than they would have before. And so you're going to hear a higher frequency, a higher pitch sound, and a shorter wavelength when it's approaching you. And when you're behind the truck, the sound waves will get spaced out, and so you're going to hear a lower frequency and it'll have a higher wavelength. So when the source of sound is moving towards you, you hear a higher frequency. If it's moving away from you, you hear a lower frequency. And that's a Doppler shift, and we've all heard this as a siren goes by us. If the source is moving towards the observer, we can calculate the frequency shift by how fast the source is moving. So this equation here shows you f prime, the new frequency, is equal to the old frequency divided by a factor that's less than 1 if it's moving towards you. So that's going to make it bigger, right? If you have a factor less than 1 in the denominator, it's going to make the number bigger. And it's smaller by a factor of the speed of the source divided by the speed of the sound. So remember, the speed of sound is about 340 meters per second. If the source is moving away from the observer, the equation changes in that the denominator has a plus sign instead of a minus sign. So we're dividing by a number bigger than 1, and so the new frequency is going to be smaller than the old frequency. What happens if you're the one that's moving? So let's say there's a siren on the ground and you're driving towards the siren. Well, the wavelength stays the same, but what's going to happen is as you're driving towards it, you're going to be cutting through those wavefronts more often than you would if you were standing still on the ground. So you're going to hear those waves passing you at a higher frequency, and so you'll hear a higher pitch sound. Same thing when you're driving away, you're going to hear them with a smaller frequency. So it depends on the relative speed between you and the source. And the equation that we have in this case is different. So the equation, so again, if you're moving towards the stationary source, you want the frequency to go up. So the new frequency is the old frequency multiplied this time by a factor that's bigger than 1. And so now we have the speed of the observer over the speed of sound. And if it's moving away, you multiply by a factor smaller than 1, so the frequency goes down. So it's 1 minus V observer over V sound. What if both of them are moving? Well, then we would combine the two equations, and what you choose for the plus or minus depends on what's going on, whether it's moving towards or away, and you have to use the similar logic to what we had in the previous equations. So let's do a couple of examples. So let's first of all talk about a moving source. So let's talk about the fire truck. It's got a siren that has a frequency of 500 hertz when it's stationary, but now it's traveling at 50 meters per second. What frequency will you hear as it approaches you and as it leaves you, assuming that the speed of sound is 343 meters per second? So we're going to use these two equations. Which one do I use? Well, I've got the source of the sound is moving, so I'm going to use the equation on the left. Okay, so I've got F prime is equal to F times 1 over 1 plus V source over V sound. And I've got the equation F prime equals F times 1 over 1 minus V source over V sound. Okay, so the speed of the source, that's the speed of the fire truck, so that's 50 meters per second. F is the frequency of the siren, which is 500 hertz. And the speed of sound is 343 meters per second. So we've got all the unknowns there. Basically, it's just a plug and chug. We just have to decide which equation do we use for approaching and which equation do we use for leaving. Well, remember, as you get closer, you hear a higher frequency. So when it approaches, we want the equation that's going to give us a number that's bigger. And to get a number that's bigger, we have to divide by something less than 1. So this bottom equation has to be the one we use for approaching. When the thing is going away from us, we hear a lower frequency. So I want to divide by something bigger than 1. So the top equation has to be the one for when it's leaving. So always think about it. If you're getting closer, you want a higher frequency, and which equation is going to give you the higher frequency, and then you'll know which to choose, the plus or the minus sign. So if it's approaching, I'm going to use the bottom equation. So I'm just going to plug my numbers in. So my new frequency is 500 times 1 over 1 minus the speed of the source, 50, over the speed of sound, 343. And I get 585.3 hertz. That's around 590 hertz. So the frequency went up by about 90 hertz. How about when it's leaving? When it's leaving, I'm going to use the top equation. Only thing that's different is I'm going to have a plus sign in the denominator. And again, remember when you're doing calculations where you got calculations in the denominator, make sure you put enough brackets into your calculator. If I do that, I get 436, or about 440 hertz. So you can see it's not a symmetrical shift. When it's approaching you, the frequency went up by 90, and when it's leaving you, it went down by about 60. So it's not symmetrical because it's a product and a quotient that we're using. Okay. Oops, looks like I had it written out. All right, let's see about a moving observer. So now you're driving at 30 meters per second towards a speaker that's emitting sounds with a frequency of 750 hertz. What frequency do you hear as you approach? And what frequency do you hear as you leave? And again, we're going to assume the speed of sound is 343 meters per second. So the frequency is 750, speed of the observer is 30, speed of sound is 343. So which equation are we going to use? Well, now we have the moving observer, so we're going to use the other equation. All right, so if it's approaching, the frequency has to go up. So which am I going to use, the plus sign or the minus sign? Well, if the frequency is going to go up, I have to multiply by something that's bigger than 1. So if it's approaching, I'm going to use f prime equals f times 1 plus the speed of the observer over the speed of sound. And if it's leaving, then I want it to get smaller, so then I'm going to use f prime as f times 1 minus the speed of the observer over the speed of sound. And so now again, it's just plug and chug. I've got everything there, and you should practice putting your numbers in. Make sure you know how to do a calculation like this. So I've got 1 plus 30 over 343 times 750, which can give me 816 hertz. And leaving, it's going to be 750 times 1 minus 30 over 343. And so that's going to go up to 684 hertz. So again, remember, when you're getting closer, it's going to go up. When you're getting further away, it's going to go down. And if you know those two rules, then you can look at the equation and figure out which you need to use, the plus sign or the minus sign. So what I want you to do for the activity, for the Doppler effect, is a matching quiz. So if you go onto Canvas, there'll be a matching quiz that asks you to match the equations 1 through 8 with the situations A through F, and you can see there's 8 equations and only 6 situations. So at the end you'll find there's 2 equations that you don't have a match for. You should think about those 2 equations and what actually happens in those 2 equations, the one that didn't match with anything. Alright, so we have a moving observer in some situations, we have a moving source. You need to figure out which equation goes with which situation.